Right, so hello and welcome everyone to the 10th week of interactive live sessions for the course CFD for Incompressible Flows. This is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras. And like every week, we shall be solving some problems together and discussing anything and everything related to the course. This week, we have started looking into finite volume methods in contrast to finite difference methods, which we have been learning so far. So let's delve into the questions. This is question number one, which is asking us what is the main difference between these two methods, the finite volume method, also known as FVM, and the finite difference method, which is FDM. Is it option A? The finite volume method discretizes the equation in terms of volumes instead of points. Option B, the finite volume method uses central difference scheme instead of forward or backward difference schemes. Or is it option C, that the finite volume method only works for one-dimensional problems? Or is it option D, that there is no practical difference between the two methods? So here we have four options. Read them carefully, and once you're convinced that this is the correct answer, you can type in the chat box, or you can unmute and answer as well, however you feel comfortable. Okay. Okay, so this is a simple question, and we have already a few quick responses in favor of option A, that the finite volume method discretizes the equation in terms of volumes instead of points. So it's a simple one. So the answer to it is correct. So option A, the finite volume method discretizes equations in terms of volumes instead of points. Now, why is that important? So, and remember, in finite difference method, it's not only that we discretize the domain into points, those points have to be orthogonally placed as well, either in a Cartesian coordinate or in any other coordinate system as well. So the problem there is that, let's say if we have a complicated geometry like this is not the least complicated to begin with. There are, you know, tremendously more complicated problems which CFD deals with. But even with a simple curved duct like this, where this is the inlet, these are the two walls on the sides, and there is this outlet over here. Modeling something as simple as this would require you to, using a finite difference method, would require you to discretize this into orthogonal points like this, where things become very difficult. Right. So first of all, conforming an orthogonal grid to such a geometry is difficult. You can see these discontinuities in such locations, right? You can identify them, and as well as applying boundary conditions becomes a nightmare. So for all those reasons, finite difference method is really limited in terms of application. It's not really used beyond some academic or some very niche simple problems. So all practical and real engineering or scientific problems would require you to either use a finite volume method, or there is another popular method known as the finite element method, or FEM. So FEM and FVM, these are the two popular and more, uh, what can I say, well accepted ways in which commercial CFD is actually done. So what happens here is that instead of discretizing into orthogonal points, we break it up into volumes, which could be or could not be, need not be orthogonal to each other. So let's say for a geometry like this, I can divide it into volumes such as this, where so within each control volume as such, so I'll just highlight this one. So you can see it's a weirdly shaped control volume, right? But all the conservation equations are actually satisfied by this control volume. So whatever flux comes in, goes out, is conserved. So we can apply the conservation equations the in a integrated fashion to this to these individual control volumes, and the aggregate of that would be good enough to represent the actual geometry. So that's why this method is so powerful. So any questions on this?
Okay, sir.
Yeah, hello. Were you trying to say something?
No, sir. It's okay, sir. Understand, sir.
All right. So if there are no questions, we'll keep moving along. We'll move on to the next question, which is asking us, what is the purpose of the flux term in the finite volume method? Is it to represent the rate of change of the physical quantity within each control volume? Is it to represent the transfer of mass, momentum, or energy across control volume boundaries? Is it option C, to represent the boundary conditions applied to the control volume? Or is it option D, to represent the source or sink terms in the equation? So I'll write down the generic equation first. So dou phi dou t plus uh, the grad of, not grad, the divergence of the flux term should be equal to the source term. Yeah. So this is the generic equation, and this is our flux term. What is it useful for? Option A, B, C, or D? Okay, we have one response in favor of uh, option B. Let's see what others have to say. Okay, another response in support of option B, to represent the transfer of mass, momentum, or energy across the control volume boundaries. This is a vector, this is also a vector, so it's the divergence of flux. Any more responses on this? Does the flux term represent the rate of change of physical quantity within each control volume? Does it represent the transfer of mass, momentum, or energy across the control volume boundaries? Or does it represent the boundary conditions applied to each control volume? Or is it option D, to represent the source or sink terms in the equation? Okay, so we have a few responses in favor of option B, that is to represent the transfer of mass, momentum, or energy across the control volume boundaries. And it is the correct answer. So if I write this down again, dou phi dou t plus the divergence of the flux term equal to the source term. So the flux term basically represents the convective flux, whatever is whatever physical quantity is being uh, convected into the control volume, minus the uh, gradient of phi uh, into whatever diffusion coefficient is involved with that particular physical quantity. So this is like, this is the convective flux, this is the diffusive flux. These two add up to the total flux, and the divergence of that flux is the flux term, which the question relates to, and that represents the transfer of any physical quantity phi. That phi could be mass, that phi could be momentum, that phi could be heat energy or any other form of energy. It could be species concentrations. It could be uh, anything like uh, what else? I think I've listed all the terms which I know. So, in case of a multi-phase flow, the discrete phase concentration could also be such a uh, quantity being convected, and not only convected plus diffuse, so flowing quantity. So the flux term represents this. The first one, to represent the rate of change of the physical quantity, this is this term, the rate of change term. This is also known as the transient term or the unsteady term or the storage term, whatever you call it. It basically represents the rate of change with respect to time in a particular control volume. So if I have a control volume like this and there is a particular physical quantity phi stored within it, how does that change with time is basically represented by this first term. And the flux term, as we saw, is the second one. It represents the transfer of these physical quantities across its boundaries. So there is a j incoming here, there is a j outgoing here. The difference between the two, this is for a 1D case. In a 2D case or a 3D case, these dimensions would increase, but the main idea remains the same. The uh, and the source term is basically represented by the source term, as we call it, so source or sink, whatever. And the third option, which says that to represent the boundary conditions applied to the control volume, this doesn't make any sense because all control volumes don't have boundary conditions associated with them. It's only the ones at the end of the at the edge of the control sorry at the edge of the computational domain, they are the ones which have boundary conditions associated with them. Okay, I hope that makes things clear. If you have any questions, please ask. Any questions on this or anything related to this? If not, we will keep moving along. We'll move on to question number 3 now, which is asking us which of the following is a disadvantage of the finite difference method, FDM, compared to the FVM, the finite volume method. Is it option A, more computationally expensive? Is it less accurate? Is it less flexible in handling complex geometries? Or it cannot handle time dependent problems, that is, unsteady problems? Okay, so this is something we discussed earlier, and we have quick responses in favor of option C. That is, it is less flexible in handling complex geometries. Yeah. So this is a no-brainer. We already discussed this, and option C is indeed the correct answer. So it's less flexible in handling complex geometries. The reason we already discussed. So if I go back to the figure I drew earlier, let's use it for a little bit of discussion. So let's say this is the ijth point, I plus 1j, this is ij plus 1, and whatnot. So I minus 1j, ij minus, sorry, this is ij minus 1. So treatment of boundary, as well as, these are usually separated by delta x, delta y, and all that, right? So fixing those distances between individual points also becomes a challenging task if you are trying to fit it to a complex geometry. Whereas a finite volume method would be able to do it with ease without tracking these individual differences. Okay. So I'll come back now. I hope there are no questions on this, right? If you have any, please don't hesitate to ask. It's basically the requirement of orthogonality in finite difference grids, which makes it unsuitable for such applications for complex geometries. Okay, so we'll move along. We'll move on to, yeah. Any questions?
Sir, with respect to this limitation, there I read somewhere about boundary fitted grids. So will that solve the problem?
The boundary fitted grids for finite difference method.
Yes, sir.
I'm not really sure. I don't know. It could be done. So the idea is that so if I have a geometry like this, I will, you know, fit the grids in such a manner that the boundary, the boundary is properly represented, right? Something like this, while maintaining them to be orthogonal. That can be done, but the bookkeeping becomes difficult because you realize that in this case, you using a uniform grid spacing is not possible, right? So you'll have to have non-uniform grids, something like
Okay,
that.
sir. Thank you.
So if you are using a non-uniform grid, then you need a separate matrix for all the delta x's and the delta y's. The bookkeeping becomes difficult. Like you need multiple matrices which are keeping track of each of them. And yeah, so another benefit of using finite volume methods is that since you are uh, using, since you are breaking it up into small control volumes and you're using the integrated conservation equation for it, they are individually, so the quantities are individually conserved in each control volume, and that adds up to the bigger control volume or the bigger computational domain as well. So these are all very easily consistent. So in finite difference methods, we saw the problem of consistency, right? So we can use different discretizing schemes, and they may or may not be consistent. In case of finite volume method, it is inherently consistent always. Okay. So this is another advantage of finite volume methods. Does that answer your question? I deviated a bit. Okay.
Yes, I got it.
Yeah. So body fitted grids in finite difference method. I'll read up on it and see if I can find something else. Okay. Any other questions? Anyone? Okay. So we'll move on to question number 4 now, which is asking us which of these terms need a surface integral. So I'll first write the terms down because the question has which of these terms and there are no terms in the question. So this is the differential form of our conservation equation, right? And in finite volume method, what we do is we integrate it over the control volume. Now, after integration, some of these terms might need a surface integral. Which one is that? Is it option A, diffusion and rate of change terms? Okay, so this is not the correct equation. I'll split it up further. So the flux term has to be split up into convective and diffusive terms. So this is the equation. These are the terms of interest.
Convection and diffusion term.
Convection and diffusion terms. So option C. Okay. So let's hear from others. Which one is it? Is it option A, diffusion and rate of change terms? Option B, convection and source terms? Option C, convection and diffusion terms? Or is it option D, diffusion and source terms? We have one answer in favor of convection and diffusion terms. Another one in favor of option C as well. Sorry. uh, so two answers in favor of option C, the convection term and diffusion term. This is the rate of change term for the purpose of naming. This is the convective term. This is the diffusive term. And this is the source term. Which one is it? Option A, B, C, or D? We have two responses in favor of option C. Let's hear from others. Is it option A, diffusion and rate of change terms? Option B, convection and source terms? Option B, convection and diffusion terms? Is it option D, diffusion and source terms? Which of these need a surface integral? Option C again. Yeah. So let's have a look at the solution. It is actually option C. So what happens is, first of all, these two terms are clubbed together. This is dot product. So these two terms are clubbed together into the flux term that we saw earlier, where J basically represents U phi minus grad of. This is a vector, by the way. Okay, so given this is the form and we integrate it with respect to volume, so the first one, dou phi dou t, remains a volume integral. This one has this form, equal to another volume integral of the source term. Now, this term, if we look closely, has a divergence of some vector, right? So we can use Gauss divergence theorem here and convert this volume integral into a surface integral. And this was over control volume. This now becomes over the control surface. And so in this way, the convection and the diffusion terms, they individually get converted into a surface integral, which is this. Any questions on this? Okay, so if there are no questions, we will keep rolling. We will move on to question number 5 now. This is asking us, which of these terms need a volume integral while modeling steady flows?
Yes, sir.
Any questions? So which of these need a volume integral? Is it option A, the convection term, option B, the diffusion term, option C, the source term, or is it option D, the rate of change term? Okay, so we got multiple responses in favor of option C, the source term. Why not option D? We saw in the previous question that these two terms will have to be surface integrals and the other two remain volume integrals. So what happened to option D? Both could be correct, right? Why not option D? Correct. So for steady flow, here reading the question was careful. So for steady flow, there won't be dou phi dou t. All the derivatives with respect to time would disappear. That's why this won't be there and the source term would be there. So that's why only option C is the correct answer. So you have to be careful. If it was a multiple option correct question, then there is a risk of selecting this one as well, but that won't be correct. Okay. Any questions on this? All right. So good. All right. So moving along, we'll move on to question number 6 now, which is asking us what is the order of accuracy of the equations as a consequence of the mean value approximation? Is it first order accurate, second order accurate, third order, or fourth order accurate? Okay, we have a quick response in favor of option B, a second order accuracy. Multiple responses, we got 2 so far. Let's hear what others have to say. So mean value approximation, what is that? So basically, if I take a 1D situation like this, I know the phi here, the phi P, and I know the phi here, the phi E, and let's say I need to find what is the phi at this boundary, phi E, for let's say flux calculation. So J is basically, so let's say in the absence of diffusion, J would basically be U into phi, right? So J at this point, point E, should be equal to UE into phi E, right? And UE is stored over here at the cell boundary because we are using staggered grids. So for staggered grids, velocities are stored at the cell faces, the face centers. But phi here is a scalar which is only stored at cell centers, not at the face center. So here what is done is that phi E is approximated as the half of phi P plus phi capital E by 2, which is its two neighbors basically. So we are assuming that if there is a difference between the two, then the difference is linear. That's all. So as a consequence of this approximation, what is the order of accuracy of the conservation equations that we get? So all our responses so far has been in favor of option B, second order. So let's have a look at the uh, solution. It is actually second order. So this can be shown by Taylor series expansions. It's a bit of a long derivation. I'm not doing it here. So it was done in the it was shown in the lectures that using Taylor series expansions, you can show that if you assume linear variation between 2 points, then the error incurred is actually order of delta x square in case of 1D, and in case of 2D 3D delta y square and delta z square would come into the picture. So whatever uh, cell size you are taking, it's a the error would be dependent on the second order. So while it was explained in the lecture, it became clear, right? If you have any doubts regarding that, you can ask now. And not only that, anything in the lecture, if you find confusing, please make a note of it and bring them up now. We can have a open discussion about it and hopefully clear things up. So coming back to this, any questions or doubts? Anyone? All right, good. So we'll move along. We'll move on to question number 7, which is a match the following type of question, which is asking us to match flux terms and source terms with cell centers and cell faces. Where are these stored in finite volume method generally? Because remember, we discussed earlier that we are using staggered grids, which are better, of course. We discussed that in detail in earlier sessions. The benefits of using staggered grids in comparison to using collocated grids. So here are basically only two options. It could be either A1B2 or A2B1. Which is it? We have an answer in favor of option B, that is A2B1. Let's hear what others have to say. Simple question, we touched upon it briefly in the previous question as well. Let's hear from everyone what they have to say. Option B again. Option B, option B. This has no option but to be correct, with such majority being in favor of it. So flux terms are stored in cell faces and source terms are stored in cell centers. So if I have a blown up control volume like this, the source term would be stored here and the flux term would be stored here. West, east. And this is at P. Point P, E, W, and so on. Any questions? Anyone? Here is again a subtle difference between finite volume and finite difference method. In finite difference method, we would store actual velocities in these two phases, right? And in this case, instead of velocities, we are storing the flux terms, which is a combination of velocity as well as uh, the physical quantity in question. And if there is diffusion, then more stuff like this and dou phi, dou x at E. Not E, but these are all west. Sorry. So instead of storing just the velocity, we are storing the flux. And remember, these are all vector quantities. U was a vector and J is also a vector. So the vector quantities we store in faces, cell faces, and scalar quantities such as this, the source term, we store in cell centers. Any questions on this? So in finite difference method, we stored pressure over here. Okay, so if there are no questions, we'll move along. So which type of boundary condition can be most easily handled by the finite volume method? Is it option A, a Dirichlet boundary condition? Is it option B, a Neumann boundary condition? Is it option C, a mixed boundary condition? Or is it option D, a periodic boundary condition? Most easily handled by the finite volume method. Is it option A, B, C, or D? Think carefully, and once you have the solution, you can type it in the chat box or you can unmute and answer as well. And if you have any confusion regarding the question, then also please uh, ask about it. We will discuss and clear things up. Okay, so let's say I have a 1D system like this. This is my entire control volume, and I've broken this up into smaller finite volumes like this. And I need to specify some boundary condition over here. Sorry, at this point, as well as at this point. So, what type of boundary condition? A Dirichlet one, a Neumann one, a mixed one, or a periodic one would be most easily handled by the finite volume method without uh, including further complexities and approximations. So we have a response in favor of
So this one is only value based, and Neumann is basically
gradient.
flux based, I mean, gradient based, and then mix of these both is cozy, and combined is basically Roman.
Yeah.
So distillate will be, I think.
So we have two responses now in favor of option B, option A, sorry, and one response in favor of option C, that is mixed boundary condition. Sorry. Okay, so let's have a look at the solution. It's actually Dirichlet boundary condition. So I'll go back to the figure I drew here, and let's say I have to fix the so this is the cell of my interest and I want to so let's say do this case wise. So Dirichlet boundary condition, I simply mention the value over here. So some, let's say, phi w I have mentioned, I know this is some constant, and there will be a fee over here, over here, over here, over here, and so on. And I can use the mean value approximations and so on and go about it. Similarly, another way of doing it would be I can mention the flux over here. So in that case, sorry, in that case, my JW over here, W, that is some constant. So this can also be handled pretty easily. Now, if I include a Neumann boundary condition, in which case I'm mentioning a gradient. So in that case, so I'm telling that the, so at this point, I'm telling that dou phi dou x at W is some constant, a known constant. Now, this is within my domain, this phi p. Now to fix dou phi dou x, I would need to create another fictitious cell over here, which will have, let's say, phi prime something, phi prime w, which is a fictitious value of phi in this ghost cell. then I can say that uh, and the difference between these two is delta x, let's say. The distance between these two is delta x. So I'll now have to say that phi p minus phi w prime divided by delta x, this is equal to this constant value, right? So this is for the Neumann case, and this was for Dirichlet. Same goes for flux as well. So I need to create additional fictitious cells outside the boundary in order to accommodate Neumann or mixed type of boundary conditions. And periodic boundary condition is also a type of a Neumann boundary condition only, where we are connecting this boundary, this boundary to this boundary. So basically it boils down to gradients, and mentioning or fixing gradients would require additional fictitious cells. That increases the cell count, the total number of cells which are being considered, and a little bit of complexity in handling it as well. Fictitious cells or ghost cells, which actually do not exist, but we need them for mathematical correctness. So does that makes it clear? Why is it more easy to handle Dirichlet boundary conditions?
Okay, sir.
Okay. So if things are clear, we'll move on. We'll move on to question number 9 now, which is asking us that explicit schemes for solving finite volume method are limited by issues regarding accuracy, stability, convergence, or option D, all of the above. What are the main challenges faced by explicit schemes for solving equations using finite volume method? Not solving finite volume method, we are not solving a method, we are solving problems with a method. Okay, so one response in favor of option A, one in favor of option B. Option C, anyone? Option B again. Any other responses? Option B again. Okay, so let's have a look at the solution. It is option B, stability. Now, the thing is, accuracy is not a problem because that is ultimately dependent on, the uh, spatial difference and the temporal difference, whichever you use, and the order in which you discretize them as well. It could be first order, second order, third order, and so on. Now, stability is the issue because explicit schemes are again governed by the CFL criterion, right? Which we saw earlier. Now, if this criterion is not met, then they would become unstable and finally lead to convergence issues as well. So, if any scheme is not stable, it's not convergent anyway. So the stability is the root cause, but if this was a multiple option correct question, then you should have chosen both option B and C, because stability issues ultimately lead to the solutions diverging away and not converging, right? Any questions on this? So this is why implicit schemes are better. And we'll move on to question number 10 now, which is telling us that implicit schemes are for solving finite volume method can use large time steps without any stability issue, right? Then why is time step size kept small in such situations? Is it to increase the accuracy of the solution? Is it to ensure stability? Is it option C, to capture the physics at small time scales? Or is it option D, none of these? Okay, so here again we have responses in favor of option A as well as option C. Any more responses, anyone? Let's see. Is it option A, to increase the accuracy of the solution? Is it option B, to ensure stability? Is it option C, to capture the physics at small time scales? Or is it option D, none of these? Okay, so we have another response in favor of option C as well. Alright, so let's have a look at the solution. It is actually option C, to capture the physics at small time scales. So let's take a unsteady problem, for example. So let's say I have a cylinder and a uniform flow approaching it at a certain Reynolds number, at a high enough Reynolds number, such that vortex shedding takes place. So von Karman vortex street forms like this, right? And there is a certain frequency associated with this vortex shedding as well. So let's say that frequency is of the order, I don't know, 10 power minus 2 hertz, or just 10 hertz, for example. So 10 hertz means the time period of it would be of the order of zero point 0.1 seconds, right? Or sorry, the time period. This is proportional to 1 by f. Now, in my simulations, if I use an implicit scheme and a time step, a very large time step, let's say I use 1 second as my time step, then will I be able to see these? Will I be able to resolve this frequency of 10 hertz? No, right? So the frequency at which I'm running my simulation, that has to be greater than or at least equal to the frequency of the system, which is 10 hertz in this case. And that's why my time step has to be at least less than or equal to 0 0.1 second. Does that make sense? Any questions on this? Okay, so if there are no questions, then that brings us to the end of today's session. Then thank you for joining.
Sir, hello.
Yeah,
Sir, can we ask question on the assignment which needs to be submitted?
which needs to be submitted. No, you can't. After you have submitted, then you can ask.
Okay. Thank you, sir.
Okay.
That could be more
Sorry.
Okay, okay. If it is that there, that could be better, but it is not there.
I'm sorry, your voice is
After
breaking up.
submission, we can discuss.
Yeah, yeah. After submission, you can.
Okay, sir.
So I think week
Okay,
eight submission
sir.
has been done now. So till week eight, we you can bring up questions from the assignment and we'll discuss them.
Thank you, sir. Thank you.
Thank you. Yeah, Ayaz, you have your hand raised.
Sir, you just showed that frequency point one and that 10 hertz.
Yeah,
Uh, that Stroll number, is it related to these things?
yeah. So Struhal number, if I remember correctly, uh, it is the system frequency and so it's basically the two time scales. There is a flow time scale and a system or any shedding time scale. It's the ratio of the two. Wait a second, I'll look this up and do this correctly. Struhal number. Yeah. So Struhal number is basically uh, FL by U in this case, or any other case also. So FL by U. So L here is the length scale of whatever problem you're dealing with. U is the velocity scale, and F is the frequency of some periodic uh, phenomena going on in the system. So basically, this becomes so 1 by F would be that system time scale tau S, and L by U is the flow time scale tau F. This is the flow time scale, and this is the system time scale. Yeah, so go ahead with your question.
So suppose this one, the flow pass cylinder,
Hmm,
if we are executing for the first time,
hmm,
we have no idea about like what will be the shedding frequency.
hmm. So if
So
it's a completely new problem, then that's true. But there has been a lot of work done on vortex shedding on cylinders. So there are basically different Reynolds number ranges given in which what flow regime would be there, whether attached vortices or shedding vortices. In case of shedding vortices, there could be correlations between the Struhal number and the Reynolds number. So
if it is like airfoil, sir, any
hmm.
airfoil, then in that case also is are the data available?
uh, you'll have to see like there is a lot of theoretical work which has gone into this over the past century or so. So even complicated geometries or something new which has not been studied before, those can also be approximated as simple cases, right? It won't give you the accurate answer, but it will give you the ballpark of within where things can be.
Yes, I got it. Okay.
So, I, if I got it correctly, then your question was going towards like if we're dealing with something exactly new, then how will we know what time step to pick? Is it?
Yes, sir. This was the query.
Yeah. So you can't determine like exactly what would be the time step after which I can't figure out the frequency or below which I can be able to. But you will get some ballpark, whether it's 10 power minus 5 or you will have to go to 10 power or whether 10 power minus 3 seconds is enough. That ballpark you can get from these theoretical approximations.
And sir, like, is it related to Reynolds number, higher Reynolds number, then cell size?
That depends. That depends on the exact case you're handling with. So not Reynolds number, it's the Courant number which is important. The CFL criterion will determine that. But to capture this frequency, you might have to go to even lower frequencies, right? So in this case, in an implicit scheme, then Courant number doesn't make any difference. But to what level of resolution you have to go to uh, pick up all these frequencies, or just to to study the physics which is going on, uh, then this idea becomes important.
And sir, for any run like on airfoils, y plus value, is it any thumb rule that we should use y plus 1 all the time or lesser than that to
So
capture the
that
drag and CL?
yeah, so that is important in case of turbulent flows. And I haven't really learned much about the turbulence modeling in CFD, so I can't really uh, tell you enough on this matter.
Okay, sir. Thank you, sir.
Okay, so thank you all. We'll meet again next week. Good night. Bye.